So we've talked in length about displacement, and let's move on now to velocity and acceleration. And probably not surprised that all we need to do is to differentiate. So once we've got our displacement function, and this is just going over things that we've already touched on, to get velocity, we differentiate. Differentiating cos, you get a minus sign, and you must take the n from in here and bring it out. To get acceleration, go through the same process, differentiate again. Now, I'll just show you that if here we end up with an n squared, obviously, if I was to write that to look more like, put the n squared at the front, and then the a cos nt plus alpha. Do you recognise that a cos nt plus alpha is a cos nt plus alpha? So actually that part of it, oh, and I lost the minus sign. Should have had a minus. Could be replaced with x, and so we could have that acceleration is minus some constant squared times displacement. Remember I said back in my video earlier that we will see situations where we start with this, where they talk about the acceleration of the particle is in terms of its displacement. And it's just nice to be aware that we'll know that it's going to go back to a sine or a cos. It's going to be simple, an example of simple harmonic motion, all those sorts of things. Or if we had started with displacement as a sine function, differentiating to get velocity, differentiating again to get acceleration, and again you get this similar situation. So if I was to write that as minus n squared a sine nt plus alpha, you can probably see that a sine nt plus alpha was our displacement, and so you could actually express acceleration in terms of displacement. Now you won't be doing that in this exercise, but it's just an awareness thing that'll make it easier than when you do move on to the exercise where you see this again. I think I'll just leave this choosing the most simple equation for the moment, because as the equations come up and we are probably going to be instructed to graph them, then we'll see for ourselves about how to choose the most simple possible equation. Yeah, and it's not a big deal. It can make a difference to the working of, if we, it just can make a difference to our actual solution, but I think it's too difficult to talk about without an example. So let's move on. I think this is one of the most important little revision or summary situations that it's really worth learning. So it talks about, and I think you saw these on Mr. Ma's video as well, that here at this point here, what sorts of things do we have happening? Well, we know that we would have maximum acceleration, because you think about it, you can press that spring up. Think of acceleration like a force. What do you know is happening to you on your hand? You know that there's quite a force because that wants to spring back down. What's happening up there in terms of how it's moving? Well, it's not moving, so its velocity is naught. And we know that when it's at that position that it's at its maximum amplitude. I'll come back to this one. It's probably not the easiest one, but down at this point, similar things happening. What happens when you pull the spring right down to this position? Again, there's quite a force on it. It wants you to let it go, and it will get back to equilibrium. So again, the force or acceleration is a maximum. Again, when it's right down here, it has stopped, and again, it's in its maximum amplitude, negative amplitude position. What's happening here, right here at equilibrium each time it passes through there? Well, clearly displacement is naught because we set it to be naught. It is moving at its fastest. I think in Mr. Ma's video he might actually say accidentally that acceleration is maximum there at one stage. So if you've come across that and you're thinking, oh, that's not what I thought, I think he does actually say that. But it is maximum velocity there, and actually there is no force either way. The particle continues to move, not because there's a force on it, but because of its, well, that's not true. Yeah, just think of it, because once something's got some speed up, and it's at its maximum speed, it's not going to stop instantly unless it's forced to. So it's doing maximum velocity at this spot, zero displacement, and zero acceleration. Like I said, I think those three situations, if you can master those and remember those, then you will find simple harmonic motion questions quite straightforward. Let's have a look at this example. A particle is moving in simple harmonic motion with displacement x equals 4 on pi sine pi t. We'd expect a trig function to define displacement in a simple harmonic motion situation. A says differentiate to find velocity and acceleration and show that acceleration can be written in the form minus m squared x. So there's nothing unusual about the differentiating to get velocity and just tidying it up. It's a nice expression. It's a cos graph. There's nothing unusual about it. Differentiating it again to get acceleration, get minus pi times 4 or 4 pi, it doesn't really matter, sine pi t. Now, the last part, to show that acceleration is minus m squared x, we have to produce x. Now, x is this, 4 on pi sine pi t. At the moment, we don't have 4 on pi. So I've got to introduce another pi into the denominator, and in order to do that I'm going to do it in the format of 1. If I want pi in the denominator, I've got to put pi in the numerator, which works out really nicely anyway, because we keep this pi here, that 4 is sitting over there, we've introduced this form of 1, pi on pi, and we've got our sine pi t. We're going to split this up such that the bottom pi in the denominator goes with the 4, the pi in the numerator goes with this pi to make a squared. So that's worked out really nicely. So there's our x, and we've got our minus n squared, and n being worth pi, or equivalent to pi. B, find the amplitude. Well, the amplitude we know is just the number in front of the displacement expression, so it would be 4 on pi. The period is determined by the number, if there is one, in front of the variable, so it's 2 pi on pi, which is 2. So how long does it take? If this is in seconds, it takes 2 seconds to complete one oscillation. The centre of the motion, there's nothing indicating in the graph, in the function that it's been pushed up or down. So equilibrium will be at x is equal to 0. Calculate the maximum speed. Now, what do we know about maximum speed? Maximum speed occurs in here, maximum speed. What else is going on with speed at that point? What's going on with these other aspects? Well, we've got that displacement is 0 or acceleration is 0. So we might use one of those, and in fact you can see I've got the displacement 0 or acceleration is 0. So I've just gone with, I think that was acceleration. It doesn't really matter because they've both got sign in them. And I've dropped out the 4 on pi because that can't ever be 0. The only way then that displacement or acceleration can be 0 is if the sign part of it is a 0. What will make that 0? Well, t would have to be a 1 or a 2. It could be a 0, but say t is equal to 1. Sub that in for the speed, and speed will be the absolute value of the velocity. And the velocity formula is this one, your 4 cos pi t, and remembering t we're subbing as 1. Cos of pi is minus 1, which would have given us minus 4, but for speed we drop the sign, so maximum speed is 4. Acceleration. Maximum acceleration occurs when v is 0, and we've gone through a similar process. I'm just aware I'm going to run out of time, so again I've taken the velocity function, but all I've done is I've taken the only part of it that can vary. 4 is 4, and that's never going to vary, so it's only going to be this part. Thinking about when cos of an angle could be 0, and we get t has to be a half. Put that into acceleration because we're finding maximum acceleration, and we're getting minus 4. The maximum distance from equilibrium, the amplitude, we know is this 4 on pi. Now, with the graphs, I thought that I would fill in the detail, but show you first that because if we're graphing displacement, because it's a fairly simple sine function, we can draw our standard sine curve. Now, we then adjust the amplitude, and so I'm going to call that now 4 on pi. I'm going to call this minus 4 on pi. We know that the period is going to be impacted. So this is not 2 pi this time. Under normal circumstance with a sine curve, completes the period in 2 pi. But this time, because of the presence of the pi, this becomes 2. So this is 1, this is 0.5, and that is 1.5. Likewise, you can see with velocity, I've drawn a cos curve, where this is going to be 4, and this is going to be minus 4, and again the period is going to be 2 pi divided by pi, which is 2, so we get our sine curve completed after 2 units, and there's our 1. Acceleration, very similar to, actually no, it's not, because it's a negative sign. So flip this or rotate it around the t-axis. Where it was positive it will now be negative, where it was negative it will now be positive, and so on. So we'll have it going as high as 4 pi and as low as minus 4 pi. It's always the number out the front. And again, its period's going to be 2. And there we have the graphs.